value and very small. And this DC value are almost the same. Because the average intensity here are almost the same intensity. Right? When it becomes darker, this value is smaller. Look at areas around here. Look at this plot. This is very, very dark plot. What's that DC value equal to? Very, very small. Right there, you see. Okay? And so on. So if you look at this, you actually see there's not much happening here. There's something happening over there, right? Because there's a large value, there's some leakage, and so on. Okay? In compression, what you do is you truncate this value, right? And you reconstruct. I'm not sure whether you see it, but the iris look very good, right? You see the blocking artifact? I'm not sure in the back, you might not see it. People in the front, can you see? They have block here, yes. Right? So those blocking artifacts come from a quantization. In this example, okay, I computed out. The size 64 by 64 is 8 bit. So that's about 32 kilobit for that particular block. After I compress, is average is about 20 to 1 compression. And in this case, you have blocking artifact. And that's to be expected. Why? Because JPEG, the way that they design JPEG, is only for 4 to 1, 6 to 1, 8 to 1. In your phone, okay? Who has phone that can have image? Most of you have phone image, right? If you take a picture, do you know how much compression they have there? It's about 4 to 1 compression. And they will not give you 8 to 1 or 16 to 1 because they want to give you a picture that looks good. And JPEG is designed to have 4 to 1, which is very, very good. 8 to 1 is pushing it. Okay? Here you have 20 to 1, we expect to see error. Okay? So the limit of JPEG is about 4, 6 to 1 compression. So here, compression on Barbara, which is a big image. We see this image before, right? Original, and this is compressed at about 15 to 1. Now, far away, it looks pretty good. But I see some artifact there, over there, and so on. Okay, it's hard to see. And also, big image easier to compress than small image in general. Okay? This is 25 to 1 and 40 to 1. Looks pretty bad. Okay, so again, this is reinforcing the fact that JPEG is designed for 8 to 1. Also, you shouldn't use it to 20 or 40. Alright. Weber transform. So the way this play appears in the other direction. Okay? But the idea here is that we use a filter bank iterated this way. We shoot it. So we have a low pass approximation and detail. Okay? In this example, I'm choosing the 97 tab low shift, which give me a very smooth basis function to construct. Okay? So this is the decomposition. That's the construction. So that's the difference between. So wavelet is a global transform. Okay? It works on the whole image. DCT is a local transform. It's worked only on block 8 by 8 block. Which one is better? Who think DCT is better for compression compared to wavelet? Again, DCT only look at a local structure, 8 by 8. No correlation between structures. The correlation is in the coding. Okay? Wavelet look at everything together. Of course, the more information you have, the better you should be able to use it. Right? So if you look at the whole image, you'll be able to do a better job. Okay? That's why wavelet win over DCT. What's the trade-off? The trade-off is this one requires much more energy. You have to load in the whole image. to do this. Okay, so that's a trade-off. So here is the same eyes, okay, blender, and that's how it looks like. It's kind of hard to see, but that's a DC value. It's pretty bright, okay. And here are different subbands. So you can see that's one, another one, a third one. So let's review how it works. That's a one level. Okay, so you have, low pass, low pass, low pass, high pass, low pass, and high pass, high pass. And you see that this one captures the horizontal information, right? That's captured the vertical, this is diagonal. And the way to do that is, there's one level to the Fourier transform. Apply one more, taking this block, okay, and you see that they're correlated. You see that if this is large, it's also large, right? And they are corresponding structure here. Okay, you can see the structure. And this is 3 levels, and so on. So that's how Weber works. So what I've done is I take the ladder, okay, the whole ladder. You can see ladder, okay, kind of hard. But this is what is this actually? The hat here, the face there, right? Okay, it's too bright. And can you see ladder here? Yes. You see the eyes here? Yeah. The feather. Okay. Can you see ladder here? Yes. See the eyes, the mouth. Okay. See ladder here? Yes. So what I'm doing here is I'm taking this guy, must scale it up. I brought that 16, you can see it. The typical is very, very, very dark. Very small, it's there. The idea of Weber coding is that you're trying to find correlation across scale. Okay? If you go this direction, that's the same direction, right? A different resolution. Go this direction, that's diagonal, the same direction but different resolution. And over here, the same way. So the idea of Weber coding is that if there's a 0 value here, very small value here, it is very likely that over here also very small, and so on. Because they're correlated. Okay? So it's the idea of 0-3 coding. What it does is it scans this guy. This half resolution one. It's searching for a very, very small value. It's at a threshold. Right? Okay? If coefficient below that threshold, it's assigned 0. And it will search for the corresponding location here. This is 1 pixel. This is 2 by 2. This is 4 by 4. We will form a tree called 0, 3. Right? So the idea here is the pixel 0, they will assign a corresponding group 0 and so on. And that is a gain encoding. And it turns out that there's a lot of small values here. I'm scaling this up by 16 to try to see it. But this is very, very small. And that is a gain. So you are taking advantage of the correlation across scale. So that's what I'm saying, right? It actually, though it's kind of coding. Okay? The artifact of JPEG is in your blocking artifact, right? The artifact of Weber is a bringing artifact. Because you have multi-resolution. So the basic function will be long when you have high resolution. So if I look at Yogi here, right? This looks like I'm drawing Yogi and then I dip it into water. It's like smearing, okay? Like the ink smear, smear, right? So you can see that at edges, which is high frequency, right? This edge is gain frequency. It's basically a very large change, right? So it's a high frequency. In compression, we truncate or we assign 0 to high frequency. Those are the one that capture detail. Okay? So the area we make this equilibrium are in area of texture and high frequency. The area that we have, X is like this. You will see I have. An area with X is like this. You see